Hey guys, so this is number 5 for 2011 final, and it's an SCI program question, and it's pretty straightforward. I'll go through it with you just so you understand everything. So the question says, configure the SCI, or the Serial Communication Interface, channel 1. Configure the SCI channel 1 of the HCS12 according to the following specification. Baud rate is 19,200, so that's important. We're going to underline that. 9-bit transmission, 8-bit data, 1-bit parity, and the parity bit is enabled and set to odd parity. Okay, and another thing to notice is channel 1. Okay, so we also note that the baud rate is defined by a 13 integer value. BR divisor stored at SCIX BDH, which is the high register of the SCI for BDH, and that's stored from SBR4 to SBR0. And then we also have SCI X, which can be any channel that you want, and we want it to be 1, and that's BDL, which means the lower register, and that's from SBR7 to 0, and that doesn't really matter. What really matters is that we have the equation that they gave us here. It's BR divisor equals to the frequency divided by 16 times the desired baud rate. So the desired baud rate we wanted, it was 19,200, and we don't know the frequency, but in question 1, it says show the calculation of BR divisors for the case where an E clock is 24 megahertz. So going into this calculation here, our desired baud rate is 19,200, okay, and we have this equation here. So our clock, E clock, was 2400 megahertz. So this is the frequency of the E clock, which is 24 megahertz, which is 24 times 10 to the 16 in hertz. You have to convert it into hertz here, and so putting that into the equation, it's 24 times 10 to the 16 divided by 16 times the desired baud rate, which was 19,200 that we wanted, and it approximately equals to 78.15. And we have to round that off to an integer value of 78 because you can't put in decimal values in terms of hex. So using our calculator, assuming that you have one of these, you're going to press mode on the top. You're going to press it twice. You're going to go to base, and you press 3, and then it's going to say H if you're in hex, and you press D for decimal, hex, binary, and then this is octagonal. And so I'm going to do 78. I'm going to press D for decimal for 78 equals, and then I'm going to press hex to get a hex value. Okay, so it's 4E. So inside of there, 78 is approximately equal to 4E, and it's 2 bytes. Right, so it's 004E for question number 5. Okay, so that's what we get here. So if the answer is 78 is approximately equal to 78, and 78 is equal to 004E. Okay, so the second question says fill the underlined space in the SCIX configuration program below. So it says move byte, the value of what are we going to put. So what we're going to put in the SCI configuration for BDH and baud rate high and baud divisor, BR divisor high and BR divisor low, is we're going to put in the high byte and the low byte. So the high byte goes to 004, and it's channel 1 because it said channel 1 in the beginning, so we're going to set that to channel 1. So just remember this, when it says whatever channel, that's going to be setting the channel for every single one of these registers inside of the SCI, the serial communication interface. Okay, so SCI1 BDH is going to be 00 because that's the that's the leftmost byte, the high byte, and then the low byte is 4E, so 4E is going to be in there and it's still channel 1. Okay, so see, it says configure the SCI controller SCIX CR1 for channel 1 to satisfy the above settings by filling in the underlined spaces in the following instruction. So it says move byte 13 SCI1 CR because we're setting up SCI 1 because it's channel 1 again, so everything. And we're going to look at our appendix over here, and in our appendix, CR1 is shown here. So this is CR1, SCIX CR1. And the reason why they put 1 and 3 is because in here, if we put, let me get a little bit of room here. If we put 1 and 3, it'll set it up so that a parity bit is selected and it's odd parity and it's 9 bits. So if you see here, the specification was that it wanted parity bit enabled, and it's set to odd parity, and it's 9-bit transmission. Okay, so in here in the appendix, you'll see that it says here that it says 1 is a start bit for 0, okay, or for 8 bits, or it's 1, and if you set that to 1, then it's excuse me, it's going to be 9 data bits and then 1 stop bit. So that's exactly what we want, because number 2 condition was 9-bit transmission, 8 data bits, and 1 parity bit, which is going to be the stop bit. A parity bit is essentially the ends of a data transmission, and I'll show you that later in the timing diagram. But in here, when you see SCI CR1, we have the 8-bit 1, 2, 3, 4 spacings, and so PE. So for M, we need to have 9 data bits, okay, and which has 1 stop bit in it, okay. So M has to be 1. Okay, so if this is M, this is PE, this is PT. Okay, all right. So with that being said, we also want, what's the other condition that we want? We also want the parity bit is enabled and the set to odd parity. Okay, so we have to enable the parity bit and we have to set it to odd parity. So going back to the SCI CR1, we go to here, so we want to set odd parity. So PT has to be 1, and we want the parity bit to be enabled. So enabled has to be 1. So this has to be 1, this has to be 1, this has to be 1, and then odd parity has to be 1. So these both have to be 1. So it has to be 1, 1. Okay? And so that's why, and what is this in hex? So if I put everything else to 0, this first one, this first bit, this first 4 is 0, 1, and these last 4 is 3, 0, 3, right? So, okay, so in here, they put 0, 1, 1, 3, and I think that's wrong. Just 1 second, let me check. So going back to our thing, 13, 2 equals the hex, and then going to binary, 0, 1, 1, 0. No, it's the same thing. So we can put 1 and 3, or you can put 0, 1, and then 0, 3. The zeros can be taken out. It doesn't really matter in this case. So you want the same thing to come out here and here, right? So you can put 0, this is an answer, and you can also put 1, 3. For safety's sake, I would say put this one here, because it shows you know exactly what positions where it's going to happen, and 0, 1, and 0, 3. Okay, and in case you forgot, this is the table again. This is 3, right, and this is 1. Okay, just for your reference. Okay, and so 1 and 3 is set for channel 1 of the SCR CR1 to fulfill all these 8-bit data and 9-bit data transmission with a parity bit, and the parity bit is enabled and it's set to odd parity. Okay, all right. So the final one is this one, D. In the figure below, draw the timing diagram when the transmission byte via the RS-232, which is the device that does the transmission, with the following settings. Start bit is recognized at the signal transition from -12 to 12. So it knows that it starts when it goes from low to high. Okay, and it says the stop bit is the stop bit as the return to -12 volts. Okay, so at the bottom here, when it goes down back to stop bit. Okay, when it goes back down to 12 volts. Okay, so what happens is it starts from low and it goes to high, right? Low to high, it says okay, that's a start, and then it waits for 8 bits from 0 to 7, 8 bits of clock time, and then at the last clock it goes to stop bit, and then when it goes back down to 12, then it stops. So that's in between here. This signals the start of the transmission, this signals the end of the transmission, and inside here is the data. Okay, and that's why it was 8 data, 1 parity bit, because 1 parity bit is on each end. Okay, so the least significant bit is transmitted first for the 8-bit transmission, and the value of the data to be transmitted is $47. Note, Each column represents the time occupied by a bit of the transmission data. This time is defined by the SCI baud rate. And this another thing, 12, positive 12 represents logic 0, and negative 12 represents logic 1. Okay, so we're going to do this now. So negative 12 represents logic 1. So these negative guys on the bottom here is 1. So 1, 1, 1. Positive 12 represents logic 0, right? 0, 0. And then go back to 1, 0. And then this is a stop. Okay, and so, and this is, what is this? 0, and this is 1. So this is odd. This is odd parity bidding, okay? And the reason why is because this one is not the same as this one, okay? So odd parity bidding means that one starts with 0, and then the other left one ends with 1, and then it signals the stop of the data transmission. So in here, the reason why they changed it, we drew it out 0. This is 1, 1, 1, 0, 0, 0, 1, 0, right? It's because we want to transmit $47, right? So going back to here, 44 and then 7, right? So it says that it says the least significant bit is transmitted first. So it's going from, so 7 is transmitted first and then 4, okay? So getting some more paper out here. So this one, so these 4 here, bit 7 to 3, no, bit 7 to 4, this guy here, this should be 7. So 0, 0, 1, 0, right? And if you notice that, is it? Okay, no, it's backwards. So the least significant bit is entered first. So, okay, anyway, so this is 0, 1, 1, 1. Okay, so if I took $, okay, so this is the answer, this is what was transferred, okay, but let's say 47, let's write down 47 first as a general rule of thumb. So it's 1, 0, 1, 1, that's 4, and then 7 is 0, 1, 1, 1. Okay, and it says, okay, so it says that the least significant byte for the 8 is transmitted first. So it should be 7 going in first. Right, okay, so 7 goes in first, which is this guy here. And it's going in from this way. Okay, so it'll go, so if I put this in, so it goes this, so the least significant goes in first, so here, like this way. Okay, so having that, we know that it goes from, so 1, so starting from here, in the timing diagram, 7 goes first, so it's going to be 1, 1, 1, 0, and then 4 is going to go in next, 0, 0, 1, 0. Okay, which is exactly what happens here, which is the answer here. Okay, so it goes into here and it fills up, so this is bit 0 all the way down to bit 7, all the way down. So if it goes, starts from bit 0 all the way down to bit 7, right? And so bit 0 is the thing that captures the first one that's coming in, okay? So 1 goes in, the other one goes in, 1 goes in, 0 goes in, 0 goes in, 0 goes in, 1 goes in, 0 goes in. So it goes in from this way, okay? And then it captures it from bit 0, captures the first thing that went in. So this one, since we're coming from the least significant byte, it's from the answer, the least significant least significant bit is transmitted first. Least significant bit is this one, right? So this one goes in first to here, okay? And again, remember that logical 0, in the beginning we would think like, okay, maybe 1 is going to be high and it's going to logical 12, right? 12, positive 12 volts. But you have to make sure you note the settings, okay? So they say that positive 12 represents 0, so you got to flip it. So if it's 1 here, then it has to be negative 12 here, okay? So just make sure you know that. And that's it. So if you have any questions, just let me know and shoot me a message. Okay, bye bye.